Hello, everybody. My name is Hartmut Kaiser. I'm working as a research professor at Louisiana State University. Whenever a new student joins the Stellar research group that I'm leading, the first question that they ask is, what should I work on? What do you want me to work on? And since one of the main software projects we're working on in the group is developing Hpx, that runtime system I want to use as a basis for my presentation today, I suggest to them why don't you pick one of those parallel algorithms we have implemented, do a thorough performance analysis, measure how it's performing, and then try to improve it. This has many benefits because the students are forced to start working on Hpx, dig into the code, understand how the algorithms are implemented. They learn to do performance measurements, which is not as simple as it might sound. You have to really know what you're doing. And in the end, they have to use the information they have gathered to improve the code, to figure out what can be improved in the implementation. So in that context, I want to start with a real-world story. When students come back, what we often see is some graphs. And this graph shows you the performance of a parallel for each run on a Intel Skylake on 64 cores and compares the speed up achieved for different input sizes. The x-axis gives you the size of the sequence the parallel for each is working on, and the y-axis gives you the speed up relative to the sequential execution time of the same input size. The numbers on the x-axis are powers of 2. So 2 to 10 means 1,000 elements, 20 means roughly 1,000,000 elements, 30 means roughly 1,000,000,000 elements. So what you can see here is that the performance that student came back with is not the worst, right? You have 64 cores, you have an average speed up of 55. The spread of the measurements are caused by cache alignment effects, which are outside of this talk, outside of the scope of this talk. That's why I put that trend line there so that you can roughly see what it is. And what I need to add is that this was measured with a compute-bound core, so compute-bound loop body, a for each that actually does a lot of computation in its body. So far, so good. Everything's kind of clear, looks nice. But then suddenly another graph is brought to the table with the very same parallel for each, with this very same benchmark, with this very same setup. But the only difference is that this for each has essentially no work in its body, essentially just one math operation or something like that. And the question is immediately, could you explain that to me? Why do we see these completely different behaviors between compute-bound and memory-bound loop bodies for a very same implementation? And while most of the students, at least, well, how can I say that? Politely, how can I say that politely? At least pretend that they have a intuition why that is correct. And they say, yeah, I would have expected that. But many students still have a problem, most of the time a problem really explaining that, why that is happening. Similarly, another measurement, you have the same parallel for each. Here was run on different numbers of cores. The different colors represent different number of cores. The experiment has been performed from 1 to 48 cores. And the interesting piece here is it's a memory-bound version of it. As you can see, it starts scaling really only for very large input sizes. But what I would like to draw your attention to is this region of the graph. So if you look at it a bit more in detail, you see that the lesser cores you use, the earlier you break even compared to the sequential execution, which is interesting, right? You run on 2 cores and you get much smaller input sizes where the parallel loop starts being more efficient than the sequential execution. Very similar question. Why is that happening? And again, the intuition is there. Yeah, kind of, yeah, I would have expected that. But really explaining what's happening is difficult in general. So what I want to do in this talk today is really try to dig deeper and to figure out what is going on. Why do we see that behavior? Then I want to use the conclusions we have from those explanations to draw conclusions on how should we design our APIs in the library so that the user can really influence these things and has full control over the execution speed and is able to find the correct parameters for a particular for loop or for a particular algorithm invocation to make it as efficient as possible. To start off with, just some conventions. There will be a bit of code on the slides, and I didn't write out all the namespaces, so I will use these namespace aliases on the slides. Okay, so let's start with a short introduction into Hpx, what it is, and how does it relate to the topic at hand. It's what's nowadays called a asynchronous many-task runtime system. Fancy word. At its heart, it's essentially a very efficient threading implementation. Very efficient in the sense that if you compare it to using things with standard threads or with P threads, it's about 2 to 3 magnitudes of orders of magnitudes faster in terms of context switching, in terms of scheduling overhead, and so on. We have built several functional layers on top of that threading implementation. One is a fully conforming standard API related to everything related to parallelism and concurrency. So we have equivalent things to std thread, std async, std future, mutex, and so on, you name it. In the end, if you have a standards conforming C++ code that uses these facilities and you change the namespace from std to Hpx, your code runs usually faster right away. So you don't have to do anything except changing namespace. We have implemented a full set of the parallel algorithms that are mandated by the recent standards, even the ones in C++ 23. Hpx provides one of the first full openly available implementations of all of the algorithms. We have added a couple of extensions there, asynchronous execution, and I will talk about that a bit. We added a full set of parallel range-based algorithms, and we have done some work on vectorizing execution policies, and I will give you some examples in the end. We have added a full set of sender-receiver implementation from what's currently being discussed for standardization, but we have implemented it in C++ 17. The reference implementation is a C++ 20 implementation, since Hpx currently requires C++ 17 only, so we have re-implemented that there. And last but not least, Hpx is a distributed runtime system, so we try to extend the standard interfaces for use on tightly coupled clusters, supercomputers. And we provide a global address space, load balancing across the nodes, uniform API for local and remote execution, and so on and so on. I want to focus today on the parallel loop, on the parallel algorithms. Just to clarify what I mean when I say parallel algorithms, everybody in the room probably has seen that list for each transform, copy, all these algorithms. And that's what I want to focus on. If you classify these algorithms, you will have several groups, and it's kind of an arbitrary classification just to make things a bit more simpler. We have these simple iterative algorithms that go over the data once, like for each copy, transform, and so on. We have iterative algorithms with a twist. Those that not only go over the data once, but also do some reduction operation, like min element, all of, find, you name it. We have scan-based algorithms, inclusive scan, exclusive scan, and so on, and kind of everything else, sorting, set operations, heap operations, rotate, and so on and so on. Again, I want to focus on these simple algorithms, not because they are simple, well, because they are simple, but mostly because the code is simple enough to fit on a slide. And all the conclusions I will draw are applicable in the same way to all of the other algorithms. So let's focus on the simple ones. Okay, we want to talk about parallel algorithms. So what does it mean? How do we parallelize these algorithms in the first place? On CPUs, what we do, we split our input sequence into pieces, and then we give one of those pieces to each of the cores to run on. The size of these pieces are theoretically arbitrary. We run the algorithms on more than one core. Each of those cores gets one of those chunks, and we perform necessary synchronization afterwards. On GPUs, things are slightly different because you usually split the input sequence into pieces that fit on a warp or on a group of GPU cores, and the rest is the same. Well, almost the same, except that on GPUs, each core works on one element of your input sequence. But again, I want to focus on the CPU side here. Christian has talked about Cocos just on a previous talk, has given an overview about how things could work on a GPU. I want to focus on the CPU here. Okay, so parallel loops. You have an input sequence, and let's start with a sequential implementation. It's always the simplest one, just to bring everybody on the same page. We just call for each, for all elements in a vector, we provide a lambda function that is being invoked for each of the elements and does something useful, hopefully. How is it implemented? Well, it's very simple. It's just a glorified loop, if you want. It goes over all elements from iterator begin to iterator end and calls a function with a result of the dereference iterator, and then it post-increments the iterator to go to the next element. As simple as that. And probably everybody has looked at the implementation in your standard library, and you have seen something like that, so not much to explain here. The standard, when it comes to parallelization, and in C++17, the standard has introduced the parallel algorithms, has done that by adding a first argument to all of the parallel algorithms. And that first argument is an execution policy. In C++17, there were 3 execution policies that have been added. One has been added in C++20, sequential, parallel, unsequenced, and parallel unsequenced execution. These execution policies, for me, convey guarantees or requirements that the loop body imposes. So it's not, if you pass par to the parallel algorithms, that doesn't mean please parallelize that. That means that my loop body allows parallelization. So my loop body doesn't have any constraints to it that prevents parallelization. In that sense, sequenced means execute in order on the current thread. Unsequenced means you can execute out of order, but please do it on the current thread, which means vectorization. Par just conveys that you can execute the iterations in arbitrary order. There is no interdependencies between the iterations. And par unseq is just a combination of that. There's no constraints imposed by the loop body, essentially. Another paper, P350, and you might be aware that the standardization goes with these papers, right, which have a P and some numbering attached to it. I'm just trying to follow those numbering here, so you can look it up later on, and the links are on the slide as well. And that paper is about integrating SIMD with parallel algorithms. So it introduces or proposes a data structure or a new execution policy, standard execution SIMD, which allows for explicit vectorization. So it's different from unseq and par-unseq in the sense that unseq and par-unseq leave it to the compiler to do the vectorization, whereas this execution policy, standard execution Simdi, enables explicit vectorization, and I will give you some details later what that means. That relies on special C++ types, which are in the standard experimental namespace. Unfortunately, the name is the same as IMD, so it's a bit confusing. And those things are available in the GCC standard library already, so you can use them today. Those were specified in the Parallelism TS version 2. It's N4808 is the last publicly available draft for that one if you want to look that up. In addition to that, HPX introduces more execution policies, namely asynchronous ones that allow asynchronous execution of your parallel algorithms, explicit parallelized vectorization, Simdi, in addition to the Simdi one, and we support executors that are attached to the execution policy using the .on member function on the execution policies. Okay, let's parallelize a loop. Let's parallelize for each. How would that look like? As I said, you split the input sequence into chunks, and then you assign these chunks to the different cores. API-wise, that looks like that. You just pass the execution policy par to the for each algorithm. And the implementation looks like that. We now have an additional first argument, which is just a type of the par thingy we are passing, which is usually parallel policy. We have to figure out the size of your input sequence. If you want to divide the input sequence into chunks, you have to know how large it is, obviously. So your iterators are better be random access. Otherwise, this operation alone is a ON operation, and you don't want to do that. And that's, by the way, the reason why the parallel algorithms are not very efficient as long as your iterator is random access. So if it's random access, everything's fine, because then this is the complexity of this operation is O1. But it's not, if it's not random access, well, obviously you have to go through the whole sequence to figure out how many elements do you have in the first place. In this case, in this implementation, I just rely on futures, just for simplicity. Any other implementation would be possible as well, but I think that is the most understandable one. So we create a vector of futures. Each of the futures represents a work on one of the chunks. We have a for loop from 0 to the number of chunks. And for each of the chunks, we call async with a lambda, and that lambda executes the sequential version of the for each on the chunk. End of story. Very simple. I specifically capitalize that num chunks value because it's kind of magic. Where does it come from? How do we decide how many chunks should we have? And by the way, this simple implementation just assumes that my input size is cleanly divisible by num chunks, just to avoid complicating the code. Async launches a new thread, same way as did async, and gives you a future that represents the result of that operation. And in the loop body, inside that lambda, as I said, you just call the sequential version of for each to do the work on one of the chunks. Very simple, very straightforward. In the end, all we have to do, we have to wait for all the futures to become ready, and then we know that our parallel loop has finished running. And this is roughly the implementation we use to generate the graphs in the very beginning. So it's fairly efficient. You can see that the overheads are relatively low. So parallelization concurrently runs sequential operations on parts of the input, at least for the CPU-based version. Iterators should be random access, as I said, otherwise the performance might just go down the drain. Num chunks is a magic number. Where do we get the number of chunks from when we want to figure that out? How should we select it? What are the criteria for the best performance? And as you have seen in the first graphs, the same number of chunks, the same implementation, everything is same, just the loop body was different, gives a completely different performance characteristics. So this is a critical piece. Num cores is another magic number. I don't even have it shown here in the code, but in the second graph I showed, when you use different number of cores for your loop execution, you get different performance behavior again. How do we select the appropriate number of cores for a particular invocation of the for loop? Even more, the for loop implementation doesn't know anything about how complex the body is. How complex is that lambda I'm passing to for each? So how should we find out what is the correct number? And there are many more parameters like that, like affinities, thread priorities, stack sizes, you name it, annotations, and all of that, where you might want to play with, you might want to get those things under control, but the current standard doesn't allow us to do that, because all you have is that execution policy you're passing to the parallel algorithms. Okay, so let's step and do a bit of background and go back to the basics, to the really fundamental things that are going on. And I have to start with Amdahl's law. And everybody here has probably heard about Amdahl's law. Which gives us a theoretical limit of how fast an application can run when only part of the application has been parallelized. Essentially, what that formula says, and I promise it's the only formula I will show you today, n is the number of cores or number of compute resources you're using to run any application, and p is a percentage of how much of your application have you been able to parallelize. So if 50% of your application is parallelized and the other 50% are sequential, then you can throw as many cores at that application as you want. You will not run faster than twice compared to the sequential execution, right? Because sequential execution is constant, you can't squeeze that, but the parallel part you can kind of reduce to a minimum, which is very surprising. You put a lot of effort into parallelizing your application, you parallelized 50% of all the code base, but your code runs theoretically not faster than twice as fast than before. If you parallelize 90%, you get factor of 10. If you parallelize 99%, you get a factor of maximum 100. And those lines on the graph on the right side just give you the asymptotic behavior of how the theoretical performance look like when you increase the number of cores. This is a big problem. Because it's not only the sequential parts you are not able to parallelize, like I/O, I don't know, setup of your application, whatever you can't really parallelize. But there are also what I call the 4 horsemen of the apocalypse that prevent us from doing efficient parallelization. It's the slow factors. S stands for starvation. That just means that you have 100 cores, but you have only 50 tasks that you can run concurrently at the same time. So the other 50 cores are just starving. They don't have any work. Latencies, everything that is somehow connected to speed of light, memory latencies, network latencies, cache coherency, latencies introduced by managing cache coherency, and so on and so on. Things you have no control over. Overheads. Overheads are the worst of all, because overheads, I define overheads as the code that has to run in order to manage parallelism. You don't have any overheads when you run sequential code, like thread creation, thread scheduling, things like that. And last but not least, waiting for contention resolution. Everybody has driven on the highway, and it was a lot of traffic, and everybody was driving 30 miles an hour only, and nobody knew why. Why? Right? There isn't anything happening, but nobody is driving full speed. Contention. And this is exactly what's happening in computers and in cores in our architecture today as well. If you have too much work for the system, everything slows down to a crawl. Okay, so let's do a thought experiment. Let's say, okay, I have 100 million tasks I want to run, each 1 microsecond. And I have theoretically the ability to combine as many tasks as I want to run on a single thread. On one end, I run each of those tasks on its own thread. That's the left side of the graph. And on the other end, I run all of the tasks in a single thread. That's the right side of the graph, essentially sequential execution. And everything in between. And what I see is that surprising behavior that when I have too little work in my threads, performance goes through the roof. And the reason for that is I have a constant, let's assume it's a constant overhead I have to introduce for each of the threads I create. And if I create a lot of threads, I have a lot of overheads. And that prevents me from running efficiently. On the other hand, when I reach a point, when I go to the right of the graph, when I make the task larger and larger and larger, I get to a point where the tasks have the same are sized such that each core has exactly one task. And if I go beyond that point to the right, I have less tasks than I have cores. And that means that things are not optimal anymore either. So that's why things go up again, to the right of that vertical line. The interesting thing here in that graph is, at least for Hpx, that splitting things in equally in as many chunks as I have cores doesn't give you the best performance. But you can see that the best performance is achieved to the left of it, if I have more chunks than I actually have cores. And it's roughly 2 to 4 times the number of cores that gives us the best performance on average on Hpx. And now you might say, hey, can't be that hard to find that minimum. Well, please pay attention to the x-axis, which is logarithmic. And when I just make it linear, you suddenly see that finding the point where I have the correct chunk size is not that simple, because it's somewhere down there, and you have to be very, very fine. You have to be able to fine-tune things very well in order to really find that optimum for your particular setup, for your particular grain size. I hope that makes sense. Okay, let's get back to our graphs. And I think we are at the point now that we can start explaining what's actually going on. Well, one thing I have to add, just to explain it, namely that because we can't know how much work is in the loop body, we had to come up with some default value for the computing the chunk sizes to be used. And we did that measurement from the previous graph and said, okay, 4 times the number of cores is a perfect value for the number of chunks. And that worked out very well, at least in Hpx. So our default inside our loop implementation is just use 4 times the number of cores for your chunks. And that explains that behavior, by the way. Because if you think about it, both graphs have been collected for 64 cores. That means all data points have been collected with 256 chunks. And when the input sizes get smaller and smaller and smaller, that means that the relative overhead that is needed to schedule one of those chunks on a new thread gets larger and larger and larger compared to the actual work that I can perform inside that I have to perform for the chunk, because the chunk gets smaller and smaller and smaller, right? I have 1,000 elements, I have 256 chunks, so each has 4 elements. And that's why in the beginning we don't see any scaling there, because the relative overhead per chunk is larger than we can kind of justify. When we get to the right, everything's fine because the amount of work in the one chunk is just great, and the relative overhead is negligible. We can neglect that. At least for the compute-bound version. For the memory-bound version, things look much worse because in the end what we are measuring is the implementation overhead of the for loop, because the loop body doesn't have any operations in it. So it becomes efficient only for very large input sizes. Equally, we can explain that picture. Same thing here. The number of chunks is 4 times the number of cores. That means that for a low number of cores, our chunks are becoming larger. Because I have less chunks, right? 2 cores, 8 chunks. 64 cores, 256 chunks. For the same input sizes. And that's why it parallelizes better for smaller core numbers compared to large core numbers. Once you understand the inner workings of these things, it's fairly easy to explain these graphs. But I still thought it might be interesting to bring these examples and to explain the problems our students have to face and have to figure out. Where do we go from here? In the second part, in the second half of this talk, I want to kind of take that information we just collected and apply that to and to explain how we decided to use that information to make design decisions in terms of implementation and in terms of APIs, so that the user has full control over these things. And if the user knows, okay, my loop is memory bound, then they can specify one set of arguments or just measure what the best possible parameters are. And for memory-bound kernels, the same case. Users can apply that. The way we decided to do that is to go with executors. Executors is something that was introduced, when was it, 2015, I think, in the standardization process. Has been discussed for a very long time. And then people decided not to go with executors, but the next new shiny thing is senders and receivers. And I will talk about senders and receivers in a minute as well. But back then, we decided to go with executors. And I still think that was a correct decision because it gives us the abstraction we need to encode how, when, and where to execute our chunks, our tasks in the parallel algorithms. So it represents an API that abstracts execution in the broadest sense. You can fire and forget tasks. You can launch a task synchronously. You can launch a task asynchronously. Just by getting a handle, you can wait on and synchronize with the task execution. It's an API that allows you to launch one task or multiple tasks in one invocation. And it allows you to do some dependency tracking between tasks. So launch this after this task has finished running or something like that. It also gives you control over the parameters of the execution. Like I said, chunk sizes, number of chunks, number of cores, what cores to use, what NUMA domain to run things on, thread attributes like annotations, priorities, affinities, and so on and so on. So let's have a look at how that looks in more detail. So in Hpx, executors abstract different task launching infrastructures, if you want. And we have two different ones at this point. Originally, we were doing all the task launching and synchronization using Hpx futures, which is a very lightweight version of what standard future represents, but semantically completely equivalent. So that's one way of doing things. And only recently we have started to look into doing the synchronization and using senders and receivers, which is, everybody's talking about them. It's a fairly complicated thing to use, and I think, I really hope it will be standardized in one way or another. But it's very low level. It's essentially if you want, a computational basis for asynchronous programming. There's some specification out there. It's the P2300 paper. It's a humongous paper, 100 pages or so, describing the innards of how senders and receivers are supposed to work. On top of that, current discussions focus on integrating senders receivers with parallel algorithms. And I will give you some insights about that in a second. In Hpx, we have used executors in the broadest sense because it's kind of the basis for launching things. So you can use executors using .on any of the execution policies. You can use it as the additional arguments to async, to data flow, which is a variation of async. Future.then can take an executor, and so on. So you just pass an executor as an additional argument, and then it will use, the implementation will use that executor to launch things. So you have full control over, by providing very small objects that represent the information about how, where, and when to launch things. Let me give you some examples. So far, it's really abstract, so let's have some examples. It's always the easiest to look at. Let's start again with the parallel for each, where we pass the par execution policy, just to tell the implementation, yeah, it's okay to parallelize things. That is the easiest of all of them. Now, let's say I have written a parallel executor that conforms to certain APIs that I can instantiate, and I associate that executor with a parallel execution policy by just saying .on my executor. And then the parallel loop will use that executor to launch the task. And I can use that to launch things on a GPU. I can use that to launch things on this number domain or on these 3 cores over there or whatever I want to do or other things I want to influence. Asynchronous execution, I mentioned it in the beginning, just by saying par task. And that creates a parallel task execution policy, which turns the execution into an asynchronous execution. That means that the for each returns right away and gives you a future that represents the end of the execution of the loop, which allows you to synchronize with it later. The par task essentially represents eager execution. So the loop starts executing right away, but it gives you a handle and you can synchronize with it later on. Sender-receiver. What if, I will not talk a lot about how senders receivers work, just as much here, just to give you some context. Senders receivers are interface specifications that allow you to combine or to build asynchronous execution chains, where essentially you build pipelines of execution. You have an object that provides data and you have an interface that consumes data, and you can combine these in arbitrary ways just by connecting a sender to a receiver and then give that output to the next receiver and so on and so on. So you build these execution chains. That means that we can use senders receivers to implement executors in some way. So if we have a sender executor, silly name, it's just an executor that uses senders and receivers to do the launching and the execution, then our for each will immediately work as well, but this time on top of senders receivers. But the most interesting thing is, if I use a sender-receiver executor with a task policy, in that case, our parallel algorithms essentially don't do anything but composing a chain of operations that, when invoked, will do the parallel for. So it's a lazy asynchronous execution. The thing you get back is a chain of operations, which then later on, when you actually trigger it, will execute the parallel for loop. It's a very interesting concept, and I believe this is very powerful because it allows to integrate the parallel algorithms into more complex asynchronous execution chains. At this point, I have to sidestep my own narrative a bit because I find it too cool to show you this code, which uses sender-receiver, predefined things like just. Just is a simple sender which sends all the values it receives as arguments to the next one, which pipes it into a for each, which is a parallel task based on the sender-receiver executor. And whatever that returns is piped into a sync wait, which triggers and waits for the result. So you see that you can use the very same API we are used to for the parallel algorithms easily and integrate that with more complicated sender-receiver asynchronous execution chains in a very nice way, and we still have full control over the execution parameters, because part of the sender-receiver proposal is schedulers, and schedulers are kind of the equivalent of what we call an executor. They allow you to define how to run things, and you can write your own scheduler, and you can attach that, and you can use it with a sender-receiver predefined execution chains, and make your for each do what you want in a very fine controlled way. Okay, so a word about Hpx executors. They are small objects that expose an API supporting launching tasks. We have 7 functions. The most important ones are, and I want to focus on async execute and bulk async execute because they are the most interesting ones. The thing is that we have built an infrastructure that your executor has to implement one function only. Just implement an async execute, and all the other functions can be composed on top of that. So let's not worry about those at this point too much. Async execute is supposed to run the given function once, and bulk async execute is supposed to run the given function n times in the current execution environment. So just as an example, let's implement a simple async execute using futures again. You create a promise, we get a future from the promise, we use the scheduler that is embedded in our executor to launch that a lambda and hand the promise to the lambda and the function to the lambda. Inside the lambda, which is run on a new thread as a new task, we invoke our function, and whatever the function returns, we use to signal our promise, which makes the future ready we have returned earlier from the async execute. So it's a very simple, straightforward implementation. Another version of the async execute is using the sender-receiver mechanics. Again, the scheduler is embedded in the executor, which is passed in, and we pipe it into a sender-receiver facility, which is called then. In other words, do this and call that function for me. And that's it. But here we don't get a future back, which represents the execution, but we get an object back, which, when triggered, will do the execution. So it's an object which type describes the operation to perform. Same example, or another example, how bulk async execute, just to give you some idea how these things work. The arguments here is the executor, then a shape object, which is essentially just a number of invocations I want, the function and the arguments I want to pass to those functions. I create a vector of results. Okay, it should be a vector of futures of results. I apologize, this is a typo on the slide. The loop launches the tasks n times, as many times as we need, using the async execute function we just saw. And in the end, we just wait for everything and we get a future back, which represents the whole execution. Very straightforward and simple again. The same if you look at an implementation with senders receivers. There's a bulk facility which is specified by P2300, which does exactly what we want. It runs the given function shape times, and that's it. And since our API is variadic and we have additional arguments, we have to package that in a lambda and call that lambda or pass that lambda to bulk, and bulk will invoke its shape times. Again, the difference in the first place, in the previous slide, we got back a single future which represents the overall execution. Here we get back an object which represents the operations that need to be performed once triggered. So the first one is kind of an eager execution because it starts running right away. And this is a lazy execution because it starts running only when I explicitly trigger it after it has returned from bulk async execute. How does our for each implementation look like if we use an executor and those APIs I just described? Again, here I have a function which calculates the number of chunks somehow magically. In the simplest case, it just takes the current number of cores, multiplies it by 4, and gives you the number of chunks. We calculate the chunk size based on that. And then we use bulk async execute to run it. Here we pass the result of bulk async execute to a wait all function, which makes sure that it returns only once the future has become ready, because the whole execution is supposed to be synchronous. And in the loop, as before, we just use for each, the sequential version of for each. Same thing as before. Note that we extract the executor from the given policy using the .executor function. So the thing we attach to the execution policy with .on is accessible later on using the .executor function. So we can pass it on to our executor interface. Here an example of how we decided to expose all these parameters I mentioned before to the user. We have created a set of these facilities. I just give you one example here, that with number of chunks, which is a facility which takes an execution policy and creates a new execution policy which carries along the given number of chunks with it. You can do the same, or we have done the same things for all the other arguments, like number of cores and so on and so on. And these facilities can do two things. Either the executor already supports controlling the number of chunks intrinsically. Then it just uses that existing functionalities. If the executor doesn't support that because it's something written by you, then it creates a wrapper around your execution, your executor, that can carry along the number of chunks. And the calculate number of chunks function, which is I marked in red here, just accesses that value that was passed in from the outside. So we can nicely control things on the user level by packaging things up into execution policies or into the executor and still extracted information from inside the loop implementations. Essentially, exactly what we wanted to achieve. We wanted to be able to control parameters on the API level, which then the implementation can use to make decisions, to optimize things, and to change parameters in the implementation. So far, so good. I promised you to give you some examples about the explicit vectorization and the Simdi execution policy. Let's talk about how loops are being vectorized. And that is orthogonal to parallelizing things. So let's talk about vectorization only. Again, you have a sequence of elements, trivial types, those that fit into your vector registers, usually ints, floats, doubles. And what the GCC implementation already has, I mentioned it, it's the std experimental Simdi type, which represents a vector register. Essentially, it's a C++ type that holds 2, 4, 8, 16 floats and overloads all the operators you ever want to use with those floating point numbers in a way that when you add these two of those instances, then the appropriate intrinsics are being generated so that the underlying code is explicitly vectorized. And that has a benefit over over automatic vectorization in the compiler because you force essentially the vectorization to happen. You're not at the mercy of the compiler to understand how you want to vectorize things. So the compiler doesn't have to understand the loop structure in order to be able to vectorize because you're explicitly controlling it, which is very powerful. So those Simdi types represent those special vector registers, essentially. By passing that Simdi execution policy, please note that's in a different namespace. That's in standard experimental Simdi and not standard execution Simdi. That's execution policy Simdi. You can pass it to for each, but now note the lambda doesn't take an integer anymore, because now the lambda is being called with one of those instances of the Simdi register. And the implementation of the loop is packaging up as many floating point values or integers as fit into one vector register into one of those Simdi instances and passes that Simdi instance to your lambda. And since all operators are overloaded, you just have normal code in your lambda and the right thing will happen. And the code will be vectorized for you. So how does it look like? We figure out what is the type of that Simdi type, because it depends on the value type of the iterator. We iterate over the space by going forward by the size of the vector register. Here we just assume that the iterator has to be contiguous. Otherwise, it wouldn't work. We create a temporary instance of that Simdi type, which loads 8 floats or 8 integers into that Simdi type. We call our lambda, and if the argument is mutable, we have to write back the possibly mutated argument into the original sequence in the for each. And so we store back the Simdi register content into the input sequence as before. Okay, so the provided lambda is called with a Simdi type instead of a single value. That comes from the Parallelism TS version 2. That type has operators overloaded to make code transition seamless. The iterator should be contiguous, obviously, otherwise you can't vectorize. And the parallel algorithms load the underlying sequence into the vector register before invoking the loop. In Hpx, additionally to the Simdi, we have implemented a parsimd, which is parallelizing and vectorizing at the same time. And we have very good results with that, and I will give you some examples in a minute. Those who were on Christian's talk just a minute ago, he mentioned linear algebra library and linear algebra proposal for the standardization, which is P1673, a free-function linear algebra interface based on BLAS, which is a proposed standard library for dense linear algebra interface. What you can do with that, you create a vector of values, you create an MD span. There will be a talk about MD span. Nevin will give a talk tomorrow, I believe. I saw Nevin here. Yeah, it's tomorrow, right? So I'm not going into details what MD span does. It's essentially a multi-dimensional version of the std span we already have, and MD span has been added to C++23, as we heard this morning. And then you call the functions of the linear algebra library. In this case, you just scale the one-dimensional data you have by 2. And that library also proposes, or that paper also proposes, to have versions for those functions that take execution policies. And that's why I'm mentioning it here, because that allows us to hook into that implementation and to use all these nice features we have in Hpx with that implementation. The current implementation is in GitHub, is available, and it has 2 backends. It has a CPU implementation that relies on TBB essentially for the parallelization, and the Cocos-based implementation so that you can do linear algebra on the GPU. We are currently working on adding a Hpx backend for that allows to use all these execution policies with linear algebra. And I'll give you some examples in a minute. So what we will add is that you can use Hpx par to parallelize using the Hpx parallel loops and the Simdi stuff I just mentioned. That allows you to vectorize the inner loops for that linear algebra library seamlessly without having to do anything manually. Okay, so how would that look like? This is a very simple 1D implementation of the linear algebra scale. Execution policy, the scalar, the coefficient, and the MD span. And we have to decide whether we actually can vectorize or not. So we have to look at certain properties of the MD span, whether the current dimension we are looking at is actually consecutive. So can we load consecutive things into a vector register or not? If it is not the case, or if the execution policy doesn't require us to do vectorization, we just turn our execution policy into something that is non-SIMD. And that's another facility we have added, is essentially functionality that allows to go between execution policies so that you can write generic code and can be sure that things are either guaranteed to be parallelized or guaranteed to be not vectorized, things like that. Or if we know that we could vectorize it, we just call the for each directly. And please note, there's one difference to the specification. The specification actually says that scale should return void. But I believe we should change that so that it returns something. Because if we used the sender-receiver versions of the Hpx execution policies, that function would return a sender-receiver object which represents the scale operation once triggered. So that would automatically integrate with the sender-receiver infrastructure so that you can use the scale operation as one of the operations in your sender-receiver execution chain. Very powerful. Another example, same thing for 2D, just for the sake of completeness, how that could look like. Here we have a vector and we create an MD span with 2 dimensions. Same interface. Here I assume that we can vectorize just to make the slide a bit simpler. We need 2 loops, right? One over the outer dimension and one over the inner dimension. I'm using a MD iterator here, which is a very simple iterator that shaves off the outermost dimension from the given MD span. And when dereferenced gives you a sub-MD span of the lower dimension. So in this case, we do a for each. The outer loop shouldn't be vectorized, but it can be parallelized. And the lambda calls the inner loop with a vectorized implementation for the for loop. Again, the inner MD iterator iterates over the innermost dimension, and the outer loop iterates over the outer dimension. Very nice code. Again, it returns something, and we don't care what it returns, so that you can use it in the context of senders receivers as one of the building blocks for more complex algorithms. I believe that is a very nice concept. Okay, so far so good. Where does that get us? This graph gives you a simple result for using two execution policies on a linear algebra scale, on a 1D linear algebra scale. The red one is just parallelizing things. And since the scale operation is memory bound, right, all it does, it multiplies one value if you want, nothing more. It starts scaling very late, only for very large input sizes, as we have seen on the previous graphs. But vectorization kicks in immediately, right away, the blue graph, right? That just gives you the performance when you use the Simdi policy on the linear algebra API. And in this case, you have 8 vector lanes, and we get vectorization performance benefit of a factor of 5, just with a very simple, straightforward implementation that doesn't even have been optimized in any way. We just use the existing loop, use that execution policy, and bam, you get a factor of 5, which is quite nice. I completely understand that in order to get optimal performance for linear algebra, you have to do tiling, you have to do a lot of optimization techniques. I just left that out for brevity here, and even with that very simple, straightforward implementation, we get quite nice results. Okay, so what are the conclusions? Using execution policies for API functions that should allow for customization of execution is a good choice, definitely. So the approach we had with C++17 and with the parallel algorithms that take the execution policy as a first argument is definitely a good choice for the user, because the users can work with that. But more customization is needed. And we have to implement that one way or another. And what I'm suggesting here is that we tie that all around the execution policy, because that is a very nice means to tie up all the parameters we need to control our execution. And the implementation can take advantage of these additional parameters that are handed through. Even for linear algebra things, where nobody has even thought of adding these parameters, but by doing so, we enable that for a broad range of APIs as long as they follow that scheme. Also, having means of running things asynchronously is important. So I have big hopes for senders receivers in one way or another, but we need to integrate that nicely with the existing APIs, and that is again where the execution policy comes in and helps us achieving that goal. Adding higher level APIs that integrate well with senders receivers is a must, because senders receivers themselves is a very low set of interfaces, fairly complicated to actually get right, to understand. So in order to make it usable for the average user in industry and in academia or in the labs, we really need higher level interfaces that allow the user to start reasoning about these things on a more coarse-grained scale. Currently, new APIs for parallel algorithms in the context of senders receivers are being discussed. I believe we don't need new APIs. We have the APIs. All we need is to think how we can integrate the existing APIs with the new stuff we want. And there's a way of doing that without too much work. Just to give you an idea, to adapt our parallel algorithm implementations that were relying on the future synchronization, to adapt them to a sender-receiver scheme that I showed you, it was work of an afternoon. So it's not too complicated to make that implementation change and add that to existing implementation after the fact. And they are telling me that I'm over time and I'm done. Thank you so much for your attention. And I'm happy to take questions. Any questions? Well, I think we have a minute or two for questions, yes. Could you come to the microphone, please?
What's the relative position of two libraries, yours, Hpx, and Cocos you mentioned in the world? Do they compete with each other? May one use other?
They don't compete. We have integration of Hpx with Cocos in two ways. You can use Cocos from inside Hpx to integrate GPU work with Hpx, and you can use Hpx as a backend for Cocos to run Cocos code on the CPU. So both ways is possible, and we don't compete with each other. Just two different domains of Cocos tries to address heterogeneous computing, GPUs. Hpx keeps itself mostly out of that game. We are mostly CPU-based, but we want to be able to launch GPU kernels and integrate it with the asynchronous execution flow in Hpx. And we have made that happen for Cocos. So you can launch a Cocos kernel from Hpx, get a future back, and synchronize it with everything else. Okay.
You mentioned Hpx threads implementation are 2 orders of magnitudes faster than standard one. Could you please give a couple of words on what it is internally? And do you have any, do you know anything if compiler providers going to change their implementations?
Well, the first question, some internals, Hpx is a user-level thread implementation. So it's a cooperative threading system. Might not be what everybody wants, because you have to be aware that it's cooperative. It's not preemptive like std threads are. In terms of whether compilers want to integrate it, I'm the wrong person to ask that question. You have to ask compiler vendors whether they want to do that or not. Okay, session is over. If you have more questions, please approach me afterwards, okay? Thank you so much.